Hello everybody, welcome to lecture 7. So this is the first, we're in week 4, this is the first lecture of week 4. The live version of it will be happening on Wednesday. This is the recorded version. So we're finishing off basically on chapter 1 today, and we're discussing the theme still of solving systems of linear equations. So we've seen a few examples at this stage, and we've seen a few of the things that can happen in the process of Gauss-Jordan elimination that we use to reduce the augmented matrix to reduced row echelon form. So here on this first slide is just a summary of basically what the possible outcomes are. So one is that the system may be inconsistent, and that means that it doesn't have a solution, that the equations in the system don't have a simultaneous solution. And the way that that makes itself known as we go through the elementary row operations is that a row will emerge in the row echelon form that has 0 entries in all of the positions corresponding to variables, but has a non-zero entry in the position corresponding to the right-hand side. So basically corresponds to an equation that says 0x plus 0y, 0 equal to something that is not 0. And such an equation obviously can't be satisfied by any assignment of values to the variables. And the conclusion in that case is that the system is inconsistent. So that occurs when, if you like, a row echelon form obtained from the augmented matrix has a leading 1 in its rightmost column, or it has a row where all the entries except the last one are zeros, but the last one's not 0. Okay, so if that happens, fine, that happens. There are systems which are inconsistent. If that doesn't happen, then it means the system is consistent, which means that it does have at least one solution, or at least some solutions. And in that case, there are basically sort of 2 things that can happen, more or less. Although, of course, you could subdivide them more if you wanted to. But one possibility is that there may be a unique solution. And if that happens, it means that every variable corresponds to, every variable is a leading variable, every variable has a leading 1 in its column in the reduced row echelon form, and those columns otherwise are full of zeros. So the form of the reduced row echelon form is exactly like this. It has in its first n-1 columns, it has basically like a copy of the identity matrix. It has a diagonal of 1s going from top left downwards, 1 for each variable. And then in the right-hand column, it has the solution, the unique solution of the system, just written into the right-hand column. So the picture like this is, remember, our reduced form of the augmented matrix still corresponds to a system of equations. So that system of equations, in its first equation, it has x1, x2, and so on. So the first equation here says x1 equal to whatever this first star is. x2 is equal to the second star, and so on. So the values of x1, x2, etc., in the unique solution of the system are just written there into the right-hand column of the reduced row echelon form, and it's extremely easy to just read them from there. Okay. And the other thing that can happen, oh yeah, sorry, I should have mentioned that possibly you could have some rows of zeros additionally at the bottom of the matrix if you're in this situation, that, you know, if you had more equations than variables to begin with, you could still have a unique solution, but there could be some rows full of zeros at the end of your reduced row echelon form. Then the other possibility is that there can be infinitely many solutions, and this occurs if the system is consistent, but not every column corresponding to a variable has a leading 1 in the reduced row echelon form. So in this case, at least 1 or more of the variables is free, and there are infinitely many solutions because the free variables can assume any value, but the values of the leading variables are then determined in terms of the free variables in a particular solution of the system. So just to illustrate these different possibilities, I'd like to have a final look at one more example of solving a system of equations. I should mention this particular example is not in the lecture notes, it's in the slides, of course, which will be available. There are some other examples in the lecture notes which are comparable to this one, but which we haven't discussed in lectures, but this one in particular is not there, but it's documented here in the slides. So it has a few parts that illustrate essentially the different possibilities that can turn up when you are solving a system of linear equations. So the first part, we are presented with this system of 3 equations with 4 variables. We're asked to solve the system. So one thing that we can consider already at this stage, just looking at that system, is it has 4 variables, but it only has 3 equations, so only 3 rows in the augmented matrix. So there are not enough rows in the augmented matrix to accommodate a leading 1 for each of the 4 variables. So we could say already at this stage, there aren't enough rows, there's not enough information basically in the 3 equations to make every variable a leading variable. So if the system is consistent, it's going to have at least one free variable. To have all variables being leading variables, you need to have enough rows in the equation to accommodate a leading one for each variable. So in this case, you need at least 4 rows. And in any case, you'd need at least as many equations as variables. Okay, so the strategy, as usual, is to reduce the augmented matrix to reduced row echelon form. I have skipped the details of that in the slide here. In case anybody wants them, let's include them. So here's the augmented matrix. And to reduce it to reduced row echelon form, we'll just add a page and go through those steps one more time in our lectures. So the augmented matrix of our system is written there. It's 1, 3, 5, minus 9, 5 in the first row. 3, minus 1, minus 5, 13, 5 in the second. And 2, minus 3, minus 8, 18, 1 in the third. And the usual strategy for Gauss-Jordan elimination, first thing we want to do is get a 1 in the top left. It comes for free in this example. So we use it to clear out the rest of column 1. So we're going to leave row 1 as it is. The entries that we are sort of targeting first are these 2 non-zero entries under that first leading 1. We want to eliminate them by subtracting suitable multiples of row 1 from subsequent rows. So from row 2, we want to turn that 3 into a 0. So we should subtract 3 times row 1 from row 2. When we do that, we get 3 minus 3 times 1. We get minus 1 minus 3 times 3. We get minus 5 minus 3 times 5. That's minus 5 minus 15. We get 13 minus 3 times minus 9. That's 13 plus 27, which is 40. And we get 5 minus 3 times 5. That's minus 10. So you can already see this example wasn't chosen randomly. It was chosen to have some nice numbers in it. Okay, and then to clear out the 2 there at the lower right, we need to subtract a multiple of row 1 from row 3. And we need to subtract 2 times row 1 from row 3, so that we'd be subtracting 2 from that 2 to make it a 0. So we get 2 minus 2 times 1, minus 3 minus 2 times 3, minus 8 minus 2 times 5, 18 minus 2 times 9, that's 18 plus 18, 1 minus 2 times 5. And now I guess we've got 2 rows here. The first column is sort of dealt with. For the moment, we're going to leave the first row alone and proceed to get a row echelon form. So next, I guess we can cancel some factors that are common to all the entries in row 2 and in row 3. So we multiply row 2 by minus 1 over 10 in order to get a leading 1 there in row 2. We can observe that 10 divides all the entries in row 2, so that's not going to cause us any problems. And similarly, we multiply row 3 by minus 1 over 9. And when we do both of those steps, we're not changing row 1. In the second row, we get 0, 1, 2, minus 4, 1. We're dividing every entry by minus 10. And in the third row, we're dividing every entry by minus 9. So we get 0, 1, 2, minus 4, and 1. So of course, if you haven't already noticed, you're certainly noticing now that rows 2 and 3 here are duplicates of each other. And that means, they basically, all the time when we're performing these row operations, we're kind of adjusting the original system of equations that we had. So we're saying now that really the equation here corresponded to row 2 and the equation corresponding to row 3 are the same equation. So we don't really have 3 independent equations. We never did in the first place, although it looked like we did. So we have when we do the next sort of obvious step, and you don't really even have to write this down if you don't want to, we can subtract row 2 from row 3, which is essentially what we would do to clear out the 1 there below the second leading 1 in the 2, 2 position. We can already see that we're going to get a row full of zeros. 1, 2, minus 4, 1. And then in the third row, we get 0, 0, 0, 0, 0. And here, this is something to be a little bit careful about when you're practicing these techniques. It's kind of tempting to think when you see 4 zeros in the columns corresponding to the 4 variables there in the third row that this is an inconsistency, but it's not necessarily. This last equation here says 0, 0x1 plus 0x2 plus 0x3 plus 0x4 equals 0. There's no inconsistency there. That equation can be satisfied. In fact, it is satisfied by any choice of the variables. So what it really means is that our 3 equations that we started with weren't really independent of each other. By applying row operations to them, we discovered that essentially one of them was already a linear combination of the other 2. We're still not at a reduced row echelon form, so let's go one step further. What prevents us now from being in a reduced row echelon form? We have two leading ones. We have a row of zeros at the bottom, that's fine. We don't have to do anything about that. We have this 3 above the second leading one. So we should clear that by subtracting 3 times row 2 from row 1. And that will not damage the pattern of leading ones that we've already achieved. So final step, row 1 goes to row 1 minus 3 times row 2. So we're rewriting row 1. We're leaving row 2 and 3 the way they are. There's row 2. There's row 3. And row 1, we're subtracting 3 times row 2 from row 1, so we get 1 minus 3 times 0, 3 minus 3 times 1, 5 minus 3 times 2, minus 9 minus 3 times minus 4, that's minus 9 plus 12, and 5 minus 3 times 1 is 2. So this is now in reduced row echelon form. And that's the reduced row echelon form from the augmented matrix of that system that we started with, of 3 equations in 4 variables. So hopefully that agrees with whatever we have on the previous slide. It does. Good. So our interpretation here, of course, is that the 4 variables, there's a kind of line there separating the right-hand side from the 4 variables. These 4 variables correspond to x1, x2, x3, and x4. The third equation has no information. It's just a bunch of 0 coefficients. And really, we only have 2 equations. The first one says x1 minus x3 plus 3x4 equals 2. We can write it as x1 equals 2 plus x3 minus 3x4, if we want to. The second equation says x2 plus 2x3 minus 4x4 equals 1. So we can write that as x2 equals 1 minus 2x3 plus 4x4. And of course, I should have said this earlier, that x1 and x2 here are our leading variables, because they're the variables whose columns in the reduced row echelon form contain leading ones, and the variables x3 and x4 are free variables. And the two equations, the two sort of non-trivial equations described by this reduced row echelon form, tell us how the values of x1 and x2 respectively must depend on the values of x3 and x4 respectively in a solution of the system. So we're going to give the parameter names t and s respectively to the values of x3 and x4 in a solution of the system, and then we can write the general solution. So here it is. So we give the parameter names t and s to the values of x3 and x4 in a solution. And so these are free to assume any value that you want. They can independently assume any value. There's nothing that specifies that there must be any kind of relationship between x3 and x4. There is a relationship between x1 and x3 and x4, and between x2 and x3 and x4. So if you give the name t to the value of x3 in a solution and the name s to the value of x4, then our first equation up here tells us that x1 is 2 plus t minus 3s. Second equation tells us that x2 is 1 minus 2t plus 4s. x3 and x4 respectively are t and s. And if you want to, I just mentioned it, you can separate this into kind of a constant part, a multiple of t and a multiple of s, and write the general solution as 2, 1, 0, 0. So that's a particular specific solution, plus any multiple of the vector 1 minus 2, 1, 0, which is multiplying t here, plus any multiple s of the vector minus 3, 4, 0, 1. So we can see, we can basically describe a solution geometrically if you want to, by starting at the point 2, 1, 0, 0 in 4-dimensional space, and adding to that any multiple of the vector 1 minus 2, 1, 0, plus any multiple of the vector minus 3, 4, 0, 1. So we're looking at kind of like a plane of vectors inside 4-dimensional space, or a plane of points there. Okay, so that's the general description of the solution of that linear system. And I guess the thing that happened here that that you can't necessarily anticipate by looking at the problem as it's posed is that really at the start there we have 3 equations, but really we only have 2 equations that have independent information. The third equation is somehow a combination of the other 2, and so one of them sort of falls out when you apply elementary row operations. Okay, anyway, that's a part of the point here, is to just indicate how you would present a general solution in a case where you have 2 free variables. Okay, here is an update to the example. So here's part 2 of the example. So this time we have 4 equations in our system. The first 3 of them, take my word for it, are the 3 that we started with in part 1 of the example. And the fourth one is new. So the first 3 there are from part 1. And I guess one of the things that I wanted to mention, because we didn't talk about it before, is just, if you have a general description of the solution to a system of equations, and let's say that has 3 variables, so there are infinitely many solutions, and then you add an extra equation into your setup, and you want simultaneous solutions now of all of them, you shouldn't really have to start all over again at the start. You should be able to kind of make use of the information that you have. And what we're saying here is, after looking at the first 3 equations, we found that there are lots of simultaneous solutions to them. There's a whole kind of plane of them. We can get them by starting with some vector, adding any multiple of some other particular vector, and any multiple of yet another particular vector. So there's loads of solutions that are simultaneous solutions to the first 3 equations. The fourth equation was added in as an extra. So we have no reason to expect that every solution of the first 3 equations would also satisfy the fourth one. On the other hand, maybe some of them do. So basically, in the general solution of the first 3 equations, we had these 2 free parameters, s and t, that were free to assume any value. So maybe adding in this fourth equation, if we want our solution to be a simultaneous solution of all 4 of them, not just the first 3, maybe that imposes some relationships on s and t, or some extra stringency on what they must satisfy. So one thing that we can do, given that in this particular setup we know the general solution of the first 3 equations, is we can basically take our description of that, put it into the fourth equation, and that's new information about what s and t would have to satisfy to give us additionally a solution of the fourth equation. So we know that the general solution of the first 3 equations looks like this. What that means is that every solution of the first 3 equations has these values for the variables x1, x2, x3, and x4 for some choice of real numbers, s and t. And actually, if you're thinking about this, a useful exercise to do is just give yourself some values of s and t, write down the actual numbers that you would get here, plug them into the equations, and satisfy yourself that they are all satisfied, and that no matter how you choose s and t, you do get a solution. Okay, in any case, the fact that we want our solution of the fourth equation to also be a solution of the first 3 means that we can take it that x1, x2, x3, and x4 have this form. So we can put those into equation 4. That will say 2 times x1. So this is the 2x1 minus x2. This is minus x2 minus 3x3. x3 is t plus 4x4 should be equal to 1. So then we get an equation involving s and t, an expression involving s and t, which must be equal to 1. It turns out to be 3 plus t minus 6s must be equal to 1 in order for the solution of the first 3 equations that's described here to also be a solution of the fourth one. So that means that the parameters s and t are no longer independently free. Each of them can still assume any value, but they have to be related to each other by the fact that 3 plus t minus 6s equals 1, or by the fact, or equivalently, that t is equal to minus 2 plus 6s. So t and s are no longer independent. If we want a solution of all 4 of these equations, t must actually depend on s in this very explicit way. And we can rewrite our solution then in terms of just s, not t anymore. So here was our general solution of the first 3. If it's additionally a solution of the fourth one, then t must be related to s by the relationship that t is equal to minus 2 plus 6s. So we can replace every appearance of t in our general solution by this description of t in terms of s, and we get a general solution involving only one parameter, one s, which we can describe. So just by replacing t by that expression, minus 2 plus 6s, this is what we end up with as the general solution of the equations in that system of 4 equations. So we still have infinitely many solutions. We only have a line of them now instead of a whole plane of them. So we're saying that every solution of these 4 equations is a point in 4-dimensional space that can be reached by starting with 0, 5, minus 2, 0, which is a solution of all 4 of those, you can check, and adding any multiple of the vector 3, minus 8, 6, 1. So essentially we're saying we can start at this point, 0, 5, minus 2, 0, and travel up and down the line whose direction is given by this vector. And every point along that line will give us a simultaneous solution of these 4 equations, and every such simultaneous solution has coordinates which represent a point on that line. Okay, so again here we have 4 equations and 4 variables. So in principle we have enough equations in terms of the number of variables to have a potentially unique solution. But we already know that the first three equations are not really independent. That, the third one doesn't carry new information compared to the first two. So you could actually delete one of the first three equations from this system and you'd still have the same solution system. Okay, so even though this system has enough equations to potentially have a unique solution, it doesn't have a unique solution. It has infinitely many solutions. Okay, so that's part two. Two more parts coming. The next one is a follow-on from that one, really. So here we have the same system, except that we've added in a fifth equation. Okay, and we know that the simultaneous solutions of the first four equations have the form that we arrived at in the last slide. And we might ask ourselves, are any of those also solutions of the fifth equation? And to answer the question, we can take our parametric description of solutions of the first four, which there it is, it depends on S, which may assume any real value for a solution of the first four equations simultaneously. So same story, we can put that into equation 5 and see if there's a value of S for which this description also is consistent with equation 5. And when you do, so we're looking for some value of S for which x1, x2, x3, x4 have this form. That means that we have a solution of the first four equations. We also want it to be a solution of the fifth equation. And when you put it into the fifth equation, of course, you've got 3 times x1, that's 3 times 3s, minus 2 times x2, that's minus 2 times 5 minus 8s, and so on. So the left-hand side becomes a linear expression just involving s. Turns out to be minus 6 plus 8s. We want that to be equal to 10, which means that 8s should be equal to 16. Whoops. 16. That's not a very good 16. Which means that s should be equal to 2. So basically, of all the different values of s to give us simultaneous solutions of the first four equations, the only one that also satisfies the fifth equation is choosing s equals 2. And then we can write down the corresponding values for x1, x2, x3, and x4 that just come from this expression with s equal to 2. So x1 is 3 times 2, which is 6. x2 is 5 minus 16, and so on. Okay, so that's the unique solution of this system of 5 equations. So if we were to write the augmented matrix of that system in the first place, without having already done sort of previous work on parts 1 and 2, we would be looking at a 5 by 5 augmented matrix, 4 columns corresponded to variables, 5 equations, and we would find that in the reduced row echelon form, all 4 of those equations would be leading variables. So we'd have like a diagonal of 4 ones, 6 minus 11, 10, 2 written into the right-hand column. And in the fifth row, we'd have a row full of zeros, which we kind of already had there in part 1. So I guess the point here is, you have infinitely many solutions of some system of equations, and adding an extra solution sort of introduces another constraint and cuts those infinitely many solutions down to maybe fewer or maybe down to just one. So in this occasion, we have a unique solution. There is one other thing that can happen, and just for completeness, let's mention it with an example of this type. So the general setup usually would be exactly this. You have some sub collection of the equations have together infinitely many simultaneous solutions. You add in an extra equation, you can determine whether there are some values of those free parameters that additionally satisfy this extra equation. Here's another version of the same setup, except this time the question is to show that the system is inconsistent. So the first 4 equations are the same as last time, and the same also as part 2, I think. Certainly the same as part 3. The fifth one is looks much the same, but turns out to be not quite the same. So same story. From the previous versions, we know that the simultaneous solutions of the first 4 equations have this form for a parameter s. And we can, as we did before, check whether there are values of s for which this is also a solution of the fifth equation. And what we get when we investigate that is, well, we've got 3 times x1 plus 2 times x2 all written in terms of s. What actually happens when we look at the coefficient of s here, we've got 9s. Here we've got minus 16s. Here we've got plus 12s. And in the last position, we've got minus 5s. So in fact, what happens is all the s's actually cancel each other and we're left with no s at all on the left-hand side. It could be that we've got sort of a 0 equals 0 type situation, or a 3 equals 3 situation, but we don't, because if you look at the constant part here, we've got 10 and we've got -4, so we've got 6 plus 12s, so 6 plus 0s on the left-hand side. And to satisfy the equation, that would have to be equal to 3, but 6 is not equal to 3. So our conclusion is that this equation, this fifth equation, is not satisfied by any simultaneous solution of the first 4 equations, so that the entire system, consisting of all 5 equations, is inconsistent. It has no solution. Okay, so that is an example which I think more or less shows all the various elements that can enter the picture when you're solving a system of linear equations and looking at, for example, general solutions where there are free variables, and also at the case where a system can be inconsistent. So it's worth practicing, I think, with further examples like these. There are certainly some of them on the first homework sheet, and more of them also in the lecture notes. So, okay, thank you very much, everyone. We're going to leave it there for this one, and see you next time. Thanks a lot.